In unstructured environments where robot motion in free space interchanges with stiff and soft contact scenarios, from a force control perspective, simpler but less accurate contact models might be preferable. For stiffness estimation, geometrical uncertainty of contact position is the biggest obstacle to achieve high-quality estimations, especially in contact with stiff environments. This problem can be addressed by estimating contact parameters resorting only to force data, without using geometric information in the estimation algorithm. Robot force control architectures are commonly designed with a positive force feedback loop to decouple robot from contact dynamics. In force control tasks, due to the noisy profile of force measurements, it is common to filter force data by a low-pass filter. When filtering the feedback force, robot dynamics is no longer decoupled from the environment dynamics. Let's see through a simple example how the inertial parameters affect the force control performance when force feedback is filtered. A one-off robot is controlled in contact by a PD controller. Robot mass is the variable parameter, while the other terms remain constant. Simulations showed that, despite linearization, systems with different masses have different performances. For the same control design, setups with small masses display a sluggish response, while large mass setups display an overdamped behavior. To have a similar force control performance, the robot effective mass needs to be taken into account in the perceived stiffness parameter, which is going to affect the force control gains. The perceived stiffness estimation is given by the contribution of two terms, one given by the force relations and another proportional to the effective mass. The first term changes the estimation based on the relation between measured, desired and estimated force. The second term updates the perceived stiffness estimation based on the end effector effective mass. In this experiment, a real robot interacts with a virtual wall, being the perceived stiffness estimation given only by force relations. The experiment can be summarized as: the robot end effector is controlled to change its orientation from a vertical posture to the robot base to an horizontal one, and then back to its initial posture, changing its effective mass. This experiment shows that effective mass and perceived stiffness are closely related. The effective mass can be seen as anticipative envelope of the first term, which improves the overall control performance. In the second experiment, the robot interacts with the virtual wall, changing its posture in contact. This experiment is performed two times, first using the virtual wall stiffness value in the control model in a perfect identification scenario. In the second run, the perceived stiffness estimation algorithm is used. As can be seen, due to force filtering, force tracking performance is improved in the second run, when the control model is adapted using the perceived stiffness estimation algorithm. In this way, the perceived stiffness can be seen not as a well-defined physical property, but as an optimization parameter to improve force control performance.